Hi everyone. Today we are going to be covering section 10.5 from the textbook, which is going to talk about comparison tests. Comparison tests are going to be a way to tell whether a series might converge or diverge. Now these are going to be a bit different than things we've talked about previously, specifically because if a series does converge, it's not actually going to tell us what the answer is. It's just going to tell us that an answer does exist, or in the case where it diverges, that there is no real number that the infinite series is converging to. So the first comparison test of the two that we are going to talk about today is what's called the divergence test. Okay, so the divergence test has two different parts to it. So if we have a series, k equals 0 to infinity of ak, and we know that the limit of the terms, k goes to infinity of ak, is not equal to 0, then the series diverges. Right, and this kind of makes sense if you think about it. So if the limit as k goes to infinity of ak is not some number, let's just say it's 1/2 as an example, right? Basically what happens as we get farther and farther along in our series is we're adding up things that are closer and closer and closer to 1/2, right? So what ends up happening is as we get larger and larger k values, we're adding up 1/2 in this case, an infinite number of times, which certainly would give me an infinite value for my series. And so in this case, it would actually show that the series is going to diverge. The second part of this is if the sum from k equals 0 to infinity of ak converges, then we know the limit has to be 0. Limit as k goes to infinity of ak equals 0. If you've studied any logic or possibly any philosophy, this is what's called the contrapositive of the statement. Basically, these two statements are the same statement, however. Okay. So one very, very, very important thing to note for this divergence test, very, 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 very important, is we can't use the divergence test to prove convergence. And this is very, very important, so I'm going to highlight it. Okay. Right, and this, I mean, with just the name itself, it makes sense that it only is able to prove divergence. So if we have this limit as k goes to infinity of ak equaling 0, it is possible that the series we have converges, and it's also possible that the series diverges. The test is inconclusive. The only time we actually get information out of this test is in the case where we actually have this limit not being 0, and so we know that it does diverge. Okay. So let's go through a couple of examples for this, and then we'll move on to our next test. So the first example, one, is going to be the sum k equals 0 to infinity of k over k plus 1. All right, so if we look at a polynomial of this, we have the limit, if we look at the limit of this, k goes to infinity of k over k plus 1. Well, in this case, right, as we talked about in section 10.2, this is going to be a polynomial over a polynomial, right? Both k and k plus 1 are polynomials. And in particular, they have the same degree, right? They're both linear. They both have this degree of 1. So we know this is actually going to be equal to the leading coefficients over the leading coefficients, or 1 over 1. So this is going to be equal to 1. 1 clearly not equal to 0, so this diverges. Okay. Let's go with another example. So example 2. Let's look at the sum as k equals 0 to infinity of 1 plus 3 to the k over 2 to the k. Now we could also prove this, this will in this case diverge, but we could also prove this using our geometric series and dividing this 2k through to both terms. However, let's prove it in this case using the divergence test. So we're looking at the limit as k goes to infinity of 1 plus 3 to the k over 2 to the k. What we can do in this case is we can divide both terms in the top by 2 to the k. So this is the limit as k goes to infinity of 1 over 2 to the k plus the limit as k goes to infinity of 3 halves to the k. So what this second term means right here is I am taking 3 halves and multiplying it by itself k times. So as k gets really, really big, this limit here is going to go off to infinity. So this actually does not exist. And so this limit is going to diverge as well, because we know that this limit is not going to be equal to 0. It's actually going to get really, really big. So in this case, we're actually adding terms that are getting bigger and bigger and bigger every time. Okay, so now I want to talk about 2 examples where the divergence test is not going to have conclusive results. So example 3 and example 4 is going to be the sum. K equals, we need to do 1 here so we don't divide by 0. K equals 1 to infinity of 1 over k. And sum from k equals 1 to infinity of 1 over k squared. Okay. Right, so we can see that the limit as k goes to infinity of 1 over k equals 0, right? I get 1 over really, really big numbers. And similarly, the limit as k goes to infinity of 1 over k squared also equals 0. Okay. So as I mentioned before, the divergence test is completely inconclusive for these 2 integrals, right? We have no idea if they're going to converge or they're going to diverge. And this is very important. And this is actually one case where one of these integrals is going to converge and one of them is going to diverge. So in particular, we're going to say, we know that this one is going to diverge. And this one actually ends up being equal to pi squared over 6, which is something we're not going to prove right away. I think we'll cover it in the section on Taylor series after the second test, and I'll show you actually how you can get this pi squared here. But this is one of those other interesting cases where it's not obvious why a pi should be here, or even a pi squared in this case. Okay. So the divergence test is inconclusive, and we can't actually draw information on these 2 examples. So this is why we are going to introduce what's called the integral test. So the integral test is going to be a way to tell if a series converges or diverges. So it's going to be a lot more powerful than the divergence test because it does give us convergence and it does give us divergence. So let's say we are interested in our sum from k equals, we'll just say a to infinity of a k. All right, so now let f of x be a continuous, so there's no gaps in it, decreasing, so negative first derivative, always going downwards, and positive function. Then either k equals a to infinity of ak, and the integral, right, integral test makes sense, a to infinity of f of x dx, either both diverge or both converge. So this is a lot more powerful than the divergence test, because if we do have this integral here converges, that means that the sum is going to converge, and vice versa, right? If the integral diverges, the sum is going to diverge. Now, one very important thing to note is they might not converge to the same value. And in general, they won't converge. There's only a very few specific functions where they will actually converge to the same value. So, in general, you can just assume actually that they aren't going to. Okay. So another important thing to note about this is we do have these three conditions on our function, right? We need it's continuous, we need it's decreasing, and we need that it's positive. And these are just things you'll need to check on your actual function, right? Decreasing means we're always going down. So decreasing, it's the same as saying it has a negative first derivative if we go out far enough. So for decreasing, we're really looking for something like f prime of x is less than 0. Or you can just say, as we put in larger and larger x values, my output will get smaller and smaller and smaller. Okay. Okay, so now let's go through those two examples of this series of 1 over k and the series of 1 over k squared using the integral test. So example 3, or I guess this is now example 4. And we are looking at the sum from k equals 1 to infinity of 1 over k first. Right, so in this case, what we can do is we can just set our function f of x is equal to 1 over x, and then we have a couple of things to check about this function. The first one is that it is continuous. 1 over x is continuous from 1 to infinity, so that checks out, right? There's no jumps or gaps in our function or any vertical asymptotes. The second thing we need to show is that it's decreasing. Now, as I said before, one of the ways to do this is to show that the first derivative is negative. The other way, which we're going to do for this problem, is to think about what happens as my x values grow larger, right? So decreasing means that as x gets bigger, my y values are going to get smaller, which is exactly actually what's happening in this case. So if I say have x equals 10, I have 0.1 as my y value, 100 is 0.01, so on and so forth. So this f of x right here, right, as we do plug in these larger x values, I am going to get smaller and smaller y value. So it is decreasing. And the last thing is that it needs to be positive, right? 1 divided by a positive number is definitely positive. So, So we need to figure out the integral from 1 to infinity of dx over x. However, right, this is one of the integrals that we have actually figured out before. This is one of these integrals of the form 1 to infinity of dx over x to the k that we talked about a few sections ago. So in particular, we already know, because we've already shown, that this integral is going to diverge. And what we can actually do in general is, if we have the sum from k equals 1 to infinity of 1 over k to the p, where p is just going to be some number, then we can use our function f of x equals 1 over x to the p. We know that this is going to be decreasing as long as our p is going to be positive. If our p is negative, right, this is going to go off to infinity, and so it will clearly diverge. But in the case where we have p as a positive number, we can use this f of x as 1 over p. And then we know that the integral from 1 to infinity of dx over x to the p converges if my p is greater than 1 and diverges if p is less than or equal to 1. And that ends up being true in this case because of my integral test. So this integral right here converges for p greater than 1 and diverges for for p less than or equal to 1. And this is known as the p-series test. P-series test. It's an integral that comes up a lot, very similar to the geometric series, but now it's the base of my exponent changing instead of actually the exponent itself. So as an example of this, if I have this sum from k equals 1 to infinity of 1 over k squared, well, we know in this case I have a p of 2. My p is greater than 1, so this is going to converge. And just right as a quick reminder that just because it converges, we don't necessarily know what value it converges to. Evaluating this integral isn't going to determine that value in this case. It's just going to tell us that there is some number that this is going to converge to. Okay, so now I want to take a just slight detour to kind of explain why the integral test works. And then we can go through a few more examples showing integrals that either converge or diverge. Okay. So the reason the integral test works is actually thinking about these as Riemann sums, or these left or these right sums. So say I have my nice function f of x, where f of k equals ak, and I have all these properties, right? F of x decreasing, continuous, and positive. Okay, so what this means, I have some function that might look like this right here. And then at all integer values, those are going to be the values of my sequence. So this is a1, this is a2, a3, a4, a5, a6. And if we look at this now, well, adding up the first 6 terms, right, is kind of like adding up the rectangles. So if I take this rectangle right here from a1 to 1, this actually has an area of a1. This one right here has an area of a2, right? It has a width of 1, height of a2. a3, a4, a5, a6, and so on and so forth. And so solving what this integral is going to be from 1 to infinity, or from 0 to infinity, depending what your bounds of your series are, is going to be very similar to solving what this integral is going to be. And this is kind of the basic reasoning why if the integral converges, the series converges, and then vice versa as well. It's because of these sums. And then you can see from these triangle things above the rectangles, these are going to be like the extra area here. Let's highlight them. that is going to be the difference between this integral and this series. And so this blue is the reason why my series does not necessarily evaluate to the same value as my integral, because the integral has this little bit of extra area on top of it, which isn't accounted for in my series. Okay, so that's why it works. Let's do just a couple more quick examples using the integral test. Okay, so let's look at the sum from k equals 1 to infinity of k over k squared plus 1. So my choice for my function is f of x is going to be x over x squared plus 1. We can see pretty clearly from this that my function is going to match up on these values right here. Okay, so we need to do a couple of things. We need to show that it's continuous. We can see from this we're never dividing by 0. We have polynomials over polynomials. So in this case, it is going to be continuous. The other thing is that it will be positive for x bigger than 1. So we'll have a positive number on the bottom. X squared plus 1 is always positive. And we will have a positive number on the top as long as my x value is positive. So this is positive. And finally, the last thing we need to do is we need to show that it is decreasing. Now, in this case, it is a bit harder to see that it's decreasing, right? My bottom is always getting bigger, but so is my top. So what I'm going to do in this case, rather than just evaluating it by thinking about what the function values might be, let's actually show that its derivative is going to be less than 0. So we want to show that f prime of x is less than 0 for x large enough. All right, we're going to use the quotient rule in this. So it's going to be the bottom times derivative of the top, so x squared times 1 minus the top times the derivative of the bottom, or x times 2x. And this is going to be all over x squared plus 1 squared. Simplifying a bit, I'm going to get a 1 minus x squared over x squared plus 1 squared. Now, this top part, as long as my x is going to be bigger than 1, right? I have 1 minus something that's going to be much bigger than 1, so the top part will be negative. And because the bottom part is squared, it will always be positive. So negative divided by positive is going to be a negative. And so this is going to actually be, why is this not working? There we go. Less than 0 for x greater than 1. And so this means we can actually use the integral test for this value. So what we want to do is we want to evaluate the integral from 1 to infinity of x over x squared plus 1 dx. Now what we can do in this is we can use a u substitution with this x squared plus 1, and this will allow us to get rid of this x dx here. So using u as x squared plus 1, du is 2x dx. If x is 1, my u value is going to be 1 squared plus 1, or 2. And then similarly, actually what we'll do in this case is we'll substitute back in so we don't have to change the bounds of this. So we have this integral now of 1/2 1 over u du, right? The integral of 1 over u is going to be the natural log of u, so we're left with 1/2 natural log of the absolute value of u, which is x squared plus 1. And we would like to evaluate this from 1 to infinity. So in particular, what we need to do, we'll introduce this new variable, the limit as a goes to infinity of 1/2 natural log x squared plus 1, evaluated from 1 to a. Plugging things in, I'm going to get 1/2 natural log of x squared plus 1, or sorry, a squared plus 1, with still this limit out in front. So the limit as a goes to infinity of 1/2 natural log of a squared plus 1 minus 1/2 natural log of 2. Well, as my a keeps getting bigger and bigger and bigger, right, this natural log, the inside of the natural log will keep getting bigger and bigger and bigger, and so my natural log itself will tend off to infinity. So this integral diverges, and so the sum diverges. And so the sum k equals 1 to infinity of k over k squared plus 1. Now, this should kind of make sense. A big part of these series is you should try to develop some type of intuition on whether they're going to converge or whether they're going to diverge. In this case, a k over a k squared plus 1, well, this is almost like k over k squared plus 1. If we think about the 1 being insignificant as k gets really, really big, which makes sense, just kind of in a hand-wavy fashion, this is going to be approximately 1 over k. We know that the sum of 1 over k is going to diverge, and so it does make sense in this case that this is going to diverge, because it's more or less summing over 1 to the k. And doing tricks like this, where we say things are approximately other things, is really good for getting this intuition about whether series are going to diverge or whether they're going to converge. And we're actually going to use intuition like this in the next section. Okay, so let's go through another example. Now the example is going to be k equals 1 to infinity of 1 over the square root of 2k minus 5. Okay, so take a second to try to guess whether you think this is going to converge or whether you think this is going to diverge. Okay, so I'm going to claim that this is probably going to diverge. The reason this is this integral is really, or this, series is really like summing over 1 over the square root of k. And we know from our p-series test, which we have up here, that this is going to be like a p to the 1/2, which is going to be in the diverges section of this. So we should kind of expect, because we have this square root of k in this problem, that we might get that our series diverges. Well, let's test this and take some integrals. So our function f of x is going to be 1 over the square root of 2k minus 5. Great. Actually, sorry, this needs to be from 3 so that we don't have any zeros, or any divisions by zeros, or square roots of negative numbers. So in this case, and this should be an x, actually, 2x minus 5. In this case, we get that it's continuous, right? There's no asymptotes from 3 to infinity. This bottom is never going to be 0. Furthermore, square roots are always positive, and so we're always have 1 over a positive number, so f of x is positive. The last thing that we always need to check in these types of problems is that this function is actually decreasing. And we can do this again in the simple way of noticing that as x gets big, this bottom part is going to get bigger, right? X bigger means the inside of the square root is bigger, and so that means the entire bottom is bigger. 1 over a bigger number is actually getting smaller, right? 1 over 10 is bigger than 1 over 100, and so this is going to be decreasing. So this is decreasing, and it's also continuous and positive. If you're not as comfortable with these arguments, arguing whether things are increasing or decreasing, you can always take a derivative and try to show that the first derivative is negative for large enough x values. That's a perfectly great way to approach these problems, and it will still get you the same answer, whatever you feel most comfortable with. Great. So we can actually use the integral test in this case, and we are looking at the integral from 3 to infinity of 1 over the square root 2x minus 5 dx. Okay, so we're looking at the limit as c approaches infinity, 3 to c, 1 over square root of 2x minus 5 dx. Now we're going to do a u substitution in this case with a u equals 2x minus 5 so that we can have simply 1 over the square root of u. So doing this, I have my du is going to be equal to a 2 dx, because the derivative of 2x minus 5 is just 2. And so I actually have this integral of 1/2 1 over the square root of u du. Again, I will substitute back in my x values so that I can keep the same bounds on my integral. A lot of times when you are dealing with these improper integrals where you're going to infinity, it's a bit easier to substitute x back in rather than actually figuring out how this c value is going to change. Okay. So in this case, we have integral of 1 over the square root of u. So this is u to the negative 1/2. Taking this integral will leave me with 2 times u to the 1/2, or the square root of u. So this is square root of u. So plugging everything back in, we still have this limit as c goes to infinity of the square root of 2x minus 5 from 3 to c. Plugging in some values, we have the limit as c goes to infinity, square root of 2c minus 5, and then minus what happens when we plug in 3. When we plug in 3, we get 6 minus 5, which is 1, and so we have the square root of 1, which is 1. Okay, and now we are at a point where we should be able to evaluate this limit. This limit right here, as c gets really big, the inside of my square root is going to grow up to infinity, and so I'm taking the square root of something that's going up to infinity, which also goes up to infinity. So in this case, it's going to diverge, both the integral and the series, because that's how the integral test works. So as kind of our intuition suggested, this series right here, this infinite series, is going to diverge. And let's do one more example of this, one with a slightly more difficult integral, but nothing too bad. So we have the sum from k equals 0 to infinity of 1 over k squared plus 4. Great. Now, we should probably expect in this case that the integral is going to converge. The reason this is this, the series is going to converge. Again, the reason this is it looks a lot like the series of 1 over x squared, which we do know converges from our p-series test. But we do actually need to go through the process of proving that it does converge. So, excuse me, we set our function equal to the same thing inside the series, so this 1 over x squared plus 4. X squared, always positive. 4 is always positive, so we're adding two positive numbers together, which means that our f of x is going to be positive. Furthermore, similar to the discussions before, as x squared gets big, the denominator is going to get bigger, which means our entire y values are going to get smaller, so it is decreasing. And again, you can show this using derivatives as well. And finally, we need to show that it's continuous, but this bottom is never going to be 0, so there's no vertical asymptote, so this is actually still going to be continuous. So this means we can use our integral test, and we're specifically interested in the integral from 0 to infinity of 1 over x squared plus 4 dx. Introducing a limit, we have the limit c goes to infinity, integral from 0 to c, 1 over x squared plus 4 dx. Okay, so if you do have an integral table handy, or you would notice that this is going to actually be equal to the limit c goes to infinity of 1/2 tan inverse of x over 2. If you also want more practice with these trigonometric substitutions, this is a pretty good problem to practice these on, right? It is not does not end up being too difficult of a trig sub that you actually need to do for this problem. And so it's good practice. But we can see either from a table of integrals, or if we go through the work, when we take the integral, we're going to get this tan inverse right here. Okay. So plugging things in, we have the limit as c goes to infinity of 1/2 tan inverse of c plus 1/2 tan inverse of 0, which is going to be 0. Or sorry, minus 1/2 tan inverse of 0, which is going to be 0. So all we're left with is this tan inverse of c over 2, and we're looking at the limit as c goes to infinity. Well, if we remember our tangent function, it looks like this, where as we get larger and larger values in it, we are getting closer and closer to this line pi over 2. This c over 2 on the inside is not going to end up mattering, because if my c is getting really big, c over 2 is certainly getting big and going off to infinity as well. So this is going to be equal to pi over 4. So because this integral converges, my sum from k equals 0 to infinity of 1 over k squared plus 4 also converges. And again, very importantly, just because we know what the value of this integral is going to be, this pi over 4, does not mean that that's going to be what this sum is equal to. This sum is not going to be equal to pi over 4. We don't actually know what the value is going to be in this case. All we know is that there is some value that this sum is going to converge to. So as we keep adding up these values, it's going to get closer and closer to some value that's not pi over 4, but it will get closer and closer